So today we're going to hear from Earl Marmar. He's going to give you an introduction to fusion energy and tell you a little bit about our vision on how we hope to achieve it. Tomorrow at the same time, but in a different room, Ann White will talk about turbulence and turbulent transport in plasmas. It's a particularly important and interesting feature of the physics that we study. On Thursday, you'll hear, if you come over to the Fusion Center in NW17, you'll hear about a very exciting idea we have for a small a device that would actually produce net fusion energy. And we're very excited about this idea. It uses some new innovative technologies, and we'll be talking about that. And then if you're interested, there'll be an opportunity of the tour of the facilities. That we have a fusion machine on campus here for those of you who are not familiar, and you're welcome to see that. To go on Tuesday and Thursday next week is a little different. For those of you who may not know, the Fusion Center and the National Magnet Lab, the Fusion Center actually grew out of the Francis Bitter Magnet Lab, and we're now back together again. And this is an opportunity for those of us who have been in fusion to learn a little bit about what's going on at the Magnet Lab in terms of structural biology and spintronics. So, of course, everybody is welcome to this, but particularly those of you from the Fusion Center who want to know what our colleagues are doing. And then Friday is inertial confinement day. We have a couple of talks, one from Mark Herman from Livermore, who will tell us about the National Ignition Facility and recent work there. And then Maria Johnson will be talking about work that we do here at MIT, basically developing diagnostics and measurement techniques for that machine. There'll also be an opportunity for a tour of the facility here on that. And then one more thing, this is kind of a specialty item for those interested, a workshop on MDS Plus, which is some data management software we use. This is rather specialized, but for those interested, I think you'll find it useful. So, I don't know. So let me introduce Earl. Earl Marmar came to us. He was educated at Princeton University, but has been here at MIT, I guess, for almost 40 years now. He went and joined the Alcator group back on Alcator A. And he worked as a graduate student and then here on the physics of impurities and edge plasmas, which is a very important topic. I think you'll appreciate a little more about that after his talk. But for the last 10 or 15 years, Earl has been the head of the Alcator project, which is the major facility we have here on campus and one of the US's major fusion facilities. So, Earl?
Okay, thanks, Martin. So good morning. I'm pleased to have this opportunity to present on behalf of my many colleagues at the Plasma Science and Fusion Center our thoughts about a faster approach to realizing fusion energy using magnetic confinement. So let's dive right into it. First, what is fusion? Quick primer for those of you who aren't fully aware. So fusion and fission are really complementary forms of nuclear energy. If you look at the binding energy of nuclei, the nuclear binding energy, as a function of how many particles are in the nucleus, this is protons plus neutrons, you find here at the very low end hydrogen, helium, lithium, up through oxygen, that the binding energy is changing rapidly as a function of how many particles you actually have in your nuclei, or how they're configured actually. So if you can take hydrogen, and in this case the heavy form of hydrogen, deuterium, which is mass 2 hydrogen, has a neutron in the nucleus as well as a proton, but chemically is basically identical to ordinary hydrogen. Combine that with an even heavier form of hydrogen called tritium, which has 2 neutrons in the nucleus as well as the proton, again chemically just like hydrogen. If you can get those guys to combine, they will make a helium nucleus, an alpha particle, and you get a lot of energy from that process. And I'll talk more about that in a minute. Nuclear fission is just the opposite process. You take very heavy nuclei, things like uranium or plutonium, and you split them, and that will happen spontaneously, or it can be induced by a neutron coming in and hitting them. And then you will make those go down to a lower mass set of products, and you will gain this energy. So the most stable isotope is here at iron. So if the world was all iron 56, there'd be no possibility of getting any nuclear energy whatsoever. So we're interested in this end of the spectrum here. How can we actually make that happen to get energy out of that process? Well, fusion has a lot of energy. Fission does too, but fusion has actually even more per mass. And fusion is about 10 million times the energy per unit mass of chemical energy. In this case, hydrocarbons, burning fossil fuels, for example, coal or natural gas or gasoline. So you get about 10 million times as much energy per mass. So that's why this is so appealing. It's one of the reasons it's so appealing. What are the actual fuels? I said that we want to combine deuterium and tritium to make helium, but there is actually almost no tritium. Tritium is naturally radioactive. It has a half-life of about 12 years. It can be produced in a fission reactor, but in only small quantities. So the actual fuel we're going to use for this process is lithium plus the deuterium, which is naturally occurring. So how do we get that? How does that work? We have to actually make the tritium using the fusion process. So here's the fusion reaction. 1 deuteron, 1 triton makes a helium nucleus plus a free neutron. And actually most of the energy comes out in the form of this neutron, although the helium nucleus also has about 1/4 or 1/5 of the energy. We feed that back into the cold deuterium-tritium fuel to sustain the reaction. The energy extraction comes out here from the neutron, which we have to capture in a blanket surrounding the reaction volume. And in that same place, we have to make the tritium, and we do that by using the neutron to actually split the lithium. That's a fission process, actually, which then makes tritium. And we also get another helium from that. So actually, the heat comes out when we heat this blanket here, and then we use that to produce electricity in a conventional balance of plant. Just like in any central station power plant, you use the heat, probably eventually convert it to steam, drive a turbine, and that makes your electricity. So the net reaction actually we're looking at is 1 deuteron plus 1 lithium nucleus gives you 2 helium nuclei, which you can then fill your kids' balloons with at a party if you want to. The fuels are abundant and widely available. This is very important. The deuterium, hydrogen, all of the hydrogen we have on Earth actually, 1 out of every 6,000 hydrogen atoms is actually a deuterium atom. You've heard of heavy water, that's D2O. You can easily pull this deuterium out of the hydrogen. Water is the most abundant source. And in fact, if you take the water flowing out of your kitchen faucet, extract the deuterium, which is 1 out of every 6,000 hydrogen atoms, and put that into a DT fusion reactor, you could fuel a 5 gigawatt fusion reactor with the deuterium coming out of your kitchen sink. What about lithium? It's widely available. This is just a listing from a recent year of the mining of lithium, which is used for a number of things, including now batteries is one of the main applications. It actually comes from brine, concentrated salts, which have a fairly high concentration of lithium. These numbers are annual production now in tons, in metric tons. Worldwide production is estimated at around 34,000 metric tons right now. The reserves that are known about are enormous. How much would we need? If we look at the world electrical consumption in a couple of years ago, it turned out to be on average 2.4 terawatts. That's 2.4 million watts. To get that from a fusion reactor, we would need about 6 terawatts thermal because of efficiencies of converting that to electricity. That would actually require only about 2% of the current annual production of lithium. So there's no problem with fuels. Anybody can have them. All we have to do is make this happen. Well, what are some of the pros and cons of actually using fusion? I've already told you about the high energy density. The reaction produces no greenhouse gases, and also other pollutants are not produced in the reaction. How about nuclear fission compared to fission? Fission is actually a great source of concentrated central power, and we're using it now. It has some challenges. One of them is that in fission you have a chain reaction which you can't turn off. So you always have to keep the cooling on in a fission reactor. And we've seen some examples, unfortunately, Fukushima the most recently, where this has been a problem. Fusion, on the other hand, this doesn't happen. It's actually really difficult to keep the reaction sustained. There's very little afterheat, so you don't have to worry about cooling your reactor after you shut it down or stop it intermittently for maintenance or whatever. You have a little bit of residual radioactivity in the fusion schemes that we envision, but compared to fission, it's about 1,000 times less, and you don't have to make long-lived radioactive waste. So you end up with things that can be dealt with in very short-term storage or burial. You don't have to worry about things like Yucca Mountain, where you need to store very toxic, very radioactive substances for hundreds of thousands of years. You don't have that problem in fusion. Control is not a safety issue. Cooling is not a safety issue. And there's also another point about the comparison. One of the issues with fission has to do with nuclear weapons. And we've seen this in the news having to do with Iran most recently. Also, you worry about other states. That's not a problem with fusion. If you've got uranium or plutonium next to your fusion reactor, you are not doing that for peaceful purposes. You cannot pretend that this is for peaceful purposes. So it's much easier to monitor, and it would not be a problem in a fusion reactor. How about compared to renewables? Wind, solar, hydro, these are very important, and in the very short term have to play a role. But they use a lot of land, they use a lot of water. They also have these problems of daily, seasonal, and regional variations, which can cause, and right now we really don't have a good energy storage solution for using these renewables in a large scale. And in fact, if you were to take the current electrical grid and provide, say, 50% of the power using wind and solar, the grid would actually be unstable. It would not actually function unless you had an equivalent amount, about actually 2 watts per watt of renewable, of power that you can call on intermittently to take up the times when you can't make enough power with the renewables. So it's actually currently not a solution for the full grid, the renewables. It's important, but it's not a solution. We need steady baseload electrical production. And fusion is one of the only possible fossil-free ways of doing that. Well, why aren't we doing it already? And this is the big con. We don't quite yet know how to do it. It turns out to be a really hard set of problems, which we've been working on. And we've made tremendous progress, but we're not quite there. And also the overall cost and pace of development have been a problem. So now, well, how do we actually make fusion happen in the laboratory? We have to confine a very hot plasma made up of this hydrogen and deuterium particles. And when you heat them up to the temperatures needed for the nuclei to collide with sufficient energy to actually stick together to overcome the electrical repulsion that is naturally there, you have to get up to temperatures of something like a few 100 million degrees. And when you do that, if you take a gas and you heat it to those temperatures, the particles ionize, and you have the fourth state of matter, a plasma. How can you hold on to that? You can't use a material container at 200 million degrees. There is no material that can take those temperatures. So instead, we have to insulate the walls of the device from the plasma using a magnetic field. At least that's what we do. That's the approach we're taking. So how does that work? If you have charged particles, which is what the plasma is made up of, electrons and the nuclei, which are positively charged ions, and if you have a magnetic field, imagine now a straight set of magnetic field lines, the electrons will go in a very tight spiral along that, and the ions will also go on a spiral. We call that the gyro motion or cyclotron motion of the particles. And they are constrained so that they can't move across the magnetic field more than the size of this orbit. However, they feel no force in the direction along the magnetic field. And at the temperatures involved, the ions are moving at over 1,000 kilometers per second. So it's really not practical to take a very long, straight magnetic field and expect that you can hold on to the plasma long enough for the fusion to happen. It turns out we need to hold on to the plasma and its energy for something of the order of 10 seconds to make this practical. So to do that, you would need a straight magnetic field which was basically the size of the Earth. So that's just not practical. That is not going to happen. But what if you take that magnetic field and you bend it into a donut shape, a toroidal shape? The torus is actually unique topologically. It's the only 3D shape where a vector field, like the magnetic field, can actually be tangent to the surface everywhere. You can't do that on a sphere. You have to have some of the vector actually sticking straight out or have a singularity. So this is a unique shape, and this is the shape we use. And if you do this, now the particles which move along the field line and not across it can keep going around and around and around. And now instead of confining them for a microsecond in a practical linear system, we can confine the plasma for many seconds. So that's what we do. And fusion energy, actually, we've made remarkable progress over the last 30 or so years. If you look from 1970 to 1995, which was the period when we've made the most progress in terms of actually making fusion energy, one measure of that is something called the triple product, which is basically the pressure times the time that you've confined the plasma, the power that you can get out of the plasma, and the energy in the plasma have actually increased exponentially and much faster than the power of computer chips, so-called Moore's law, where you get a doubling every couple of years, roughly. That's Moore's law. This is the progress we've made in fusion energy over that time period. More than 12 orders of magnitude increase in fusion energy per pulse. So what happened after 1995? Progress has actually slowed. And right now, internationally, there's a very large project called ITER, which is under construction in southern France. It's not expected to be operating until after 2030. And if we put it on that same plot, we can see that this slope has really quite dramatically decreased. It's not zero, and we do expect progress, but this is rather slow, in my opinion, and we need to figure out how to speed that up. Why did that happen? Well, one thing that happened is that actually research funding has been decreased in the US particularly over the last 15 or 20 years. And also the unit size of devices being designed and built is large, as embodied in the ITER device, which is about 10 times the volume of anything that we had built before. Yes, about 10 times the volume. That makes it very costly. That makes people also very cautious. Because it's such a large investment, you have to be extraordinarily sure that it's going to work. That makes it a very slow process to actually make that actually make that come into existence. So that's slow. What can we do about that? And why do we need to do something about it? Well, one very pressing reason is that the need is actually extraordinarily urgent. This is just a movie that the New York Times published a couple of months ago. There are something like 10,000 of these rivers currently flowing in Greenland. It doesn't mean Greenland's ice cap is going to melt today or this year, but that process is underway. And that's going to lead to some pretty dramatic challenges worldwide. So we need to do something to stop the increase of CO2 in the atmosphere. How can fusion best contribute? In a timely way to this need for a carbon-free energy source. So I'm going to tell you about what we've been thinking about here at MIT to take advantage of recent technical breakthroughs to actually speed this whole process up and get to a practical realization of fusion energy in a much shorter time scale. We have recognized for a long time that high magnetic field is a very good way to get to what we call a burning plasma. A burning plasma means that the plasma is self-heated by the fusion process itself. So we're not pouring a lot of power in from the outside world to heat the plasma. We have to do that. We need a match to light the reactor. But once it's going, most of the power to make the plasma actually stay hot, to heat up the cool fuel that you feed in, is provided by the fusion reaction itself. So we call that a burning plasma. And it's the alpha particles in the plasma that actually provide that heat. By going to high magnetic field, we can do that in a relatively compact device. And these are just 4 designs that date back to the 1980s. And these would have worked. They haven't been built, but they would have done the job to get to the burning plasma. But they will not get you to the next step of making electricity. And the reason for that is that they all used copper magnets to make the magnetic field. Copper is a very good conductor, one of the best ones we have, but it's not a perfect conductor. So it takes a lot of power to run the magnets to make the magnetic field that you need to confine the plasma. And in fact, in these designs, it takes hundreds of megawatts, typically, of electrical power just to sustain the magnetic field. Also, these devices were all pulsed. They were all designed to run for somewhere between 10 and 50 seconds. And then you had to stop and cool the magnets down. That's no way to run a power plant. That would not work. And in any event, the power you need to run the magnet is so high, you will never make net electricity with this approach. But we could have studied the science. There were various reasons these things never got built. One was that people thought that because the fields were not achievable with superconductors, which actually have infinite conductivity, they require no power to sustain the magnetic field. Because these were with copper, some people said, well, this is a dead end. We shouldn't pursue this. We need to only think about superconducting facilities. And that's what ITER is. And actually, ITER, in some sense, grew out of this process of examining these alternatives. And because it was a worldwide consortium, people thought it would be economically reasonable for each country to put in their share and get to this burning plasma study, which is really important on the path to fusion energy, no question, but it doesn't get you all the way there. So we know that high magnetic field is really good. Why is high magnetic field good? If we go back to the plot that I showed you here, when you raise the magnetic field, the size of this spiral, of this orbit, the radius, gets smaller. And in fact, it's inversely proportional to the strength of the magnetic field. So if you double the magnetic field, the size of this orbit gets half as big. Why is that important? Well, if you think about the time it takes the energy to escape from a finite-sized box, it depends critically and in fact linearly on the size of this orbit, because that's the scale size over which the energy is being smeared by these orbits. So if you double the magnetic field, basically you can 1/2 the linear size of the device given fixed parameters, fusion parameters. Well, that factor of 2 is extraordinarily important, because a factor of 2 in linear size is almost a factor of 10 in volume, which means about a factor of 10 in facility cost and also ease of construction. So how can we get there? Well, there's been a basically revolution in the technology of superconducting magnets in the last few years. These are based on a physics discovery from the 1980s called high temperature superconductivity, where people in the lab doing solid state physics discovered materials. They're actually ceramics, which had this remarkable property that they went superconducting at relatively high temperature, even liquid nitrogen temperature. Ordinary conventional superconductors require liquid helium temperature, which is 4 degrees absolute Kelvin. They're very hard to work with, but more importantly, they have a magnetic field limit above which they go normal. They are no longer superconducting. And that's actually shown here. There's a critical current density that you can run in the magnet, which is a function of the field on the magnet, on the material. And this is a conventional, this is the most advanced low temperature superconductor called niobium-310, which is superconducting at liquid helium temperatures and below. And there's this very sharp drop off as a function of magnetic field above which that material is no longer superconducting. So if you're designing your fusion experiment out of niobium-310, you have to keep your maximum field basically down in this range, about a little above 10 Tesla, which is about 20,000 times the Earth's magnetic field. 200,000 times the Earth's magnetic field, sorry. And that, in fact, is what ITER is based on. The ITER design is right here in the middle of that ellipse. And that's why ITER is so big. It has a diameter of about 20 meters. And that's because of the magnetic field at the center of the plasma is actually limited to a little less than half of this value. And the gyro orbit is the size it is, so you've got to make the machine big enough to confine the plasma long enough to make the fusion happen. But if we could double the field, we could make the machine half the size. So that's what we want to do. And this discovery has now been pushed to where it's really a commercial product. You can buy these materials. They're called Rebco. And one of them is an yttrium barium copper oxide, these ceramics that I told you about. And they stay superconducting at very high current density, independent basically of the magnetic field, out to very high magnetic fields. So we can imagine designing a facility which takes advantage of this, and that's what we want to do. There's another very important advantage here as well. They are high temperature as well as high field superconductors. High temperature really matters a lot too, because it means the cooling is much easier to do. We can run these magnets at perhaps 30 degrees Kelvin compared to, say, 4 degrees or lower for the conventional superconductors. Well, maybe that doesn't sound like a huge win to you, but it turns out that the thermal properties, in particular heat capacities of materials, are very nonlinear in the temperature at very low temperatures. And by going from 4 degrees to 30 degrees K, the cooling problem, to keep the magnet cool just from its thermal conductivity losses, is enormously eased. So the engineering design becomes much simpler from the thermal point of view. So that's another big advantage that we want to utilize in designing a new facility. So where does all of this take us? I've said that there's industrial maturity of these high field superconductors. I'll tell you more about that in a minute. And that really motivates us to reconsider the whole path, the whole approach that we're taking here. We can now think of a device that would produce net electricity that would be even less than half the size of ITER, which does not produce any net electricity, by the way. It just studies the burning plasma piece of the problem. And we could do this more quickly and at lower cost, substantially lower cost. The operating point, because we go to high field, also turns out to be more stable. These plasmas have a lot of free energy because of the very strong temperature and density gradients. They become naturally very turbulent. And if you go above a certain pressure, they actually become totally unstable and they basically dissipate to the walls in under a millisecond, under a thousandth of a second. By going to higher field, you actually win yourself more margin against those kinds of instabilities. And I've also talked about this advantage of higher temperature. There's another very big advantage that comes with this. We can now think about making these magnets with demountable joints. That turns out to have a huge effect on implications for maintenance of a nuclear device like this. And I'll talk more about that later. And here at MIT, we've got research going on into how can you make these joints actually real. This is just an outline of the rest of my talk. So first, what about these superconductors? Well, these are actually pictures of the real actual tape that you can buy. It's commercially available. And we're actually making a prototype coil right now, which will give us, with just these two pancakes, 10 Tesla in the center of this coil. This is still a bit smaller. Well, it's quite a bit smaller than we need for a fusion reactor, but it's a great first step. And that, because of this tape is very flexible, it has other advantages. It's very strong as well because of the way it's made up. The actual conductor is right here. It's 1% of the thickness of this tape. Everything else is just structure to hold the thing together and some copper to stabilize it against a certain event where if you actually do heat the material with current, it will go normal, and you have to have a place for the current to go. And so that's what this copper is for. But these are very robust tapes that you can then wind into coils. So we're doing that now in our lab on the other side of campus. This is compared with the conventional superconductors where you actually have to take the material, you have to combine it into very complicated strand systems. You have to then wind your magnets, and after you've done all that, you have to heat the material up to extremely high temperature because when it's a superconductor, it's very brittle and you can't bend it anymore. And so it makes it a very complicated process. But even more important, you're stuck at the lower magnetic field with the conventional superconductors. So people are already using these tapes and this material. And this is just a few applications. There is a demonstration using this for power transmission at a power station in Long Island. This just shows the comparison of magnetic resonance imaging, in this case of a mouse, probably no longer living, I would guess, but I don't know. And they compared using a copper trim coil on the MRI system to using the high temperature superconductors. And you can see even here there's a dramatic increase in resolution. And one of the big applications actually of this new material is going to be to very high field magnetic resonance imaging systems for biological studies actually. People have also looked at using them as a potential to upgrade the Large Hadron Collider. You've probably heard of the LHC, which is the largest particle accelerator operating in Switzerland, an international collaboration. And it is based on the conventional superconductors. But if you go to these new higher field superconductors, for exactly the same reason that we can confine our plasma at higher temperatures for longer times with higher field, if you can raise the field in the particle accelerator, you can accelerate the particles to higher energy and they will stay inside the tunnel. It's exactly the same physics. Only in their case, the radius is the radius of the tunnel, which is kilometers. But it's exactly the same physics. So people have proposed replacing those coils with high temperature superconductor to get to higher energies. What about practical applications where people are actually using these for MRI systems? This is a collaboration among the people from the National High Magnetic Field Laboratory in Florida, Florida State University, one of the manufacturers of the material, and a group here at MIT. And last April, they actually had a new world record for magnetic field in a small bore coil, a solenoid. The bore is down the middle here, and it's just a few centimeters. But they got up to above 26 Tesla, which is where you need to operate for the kinds of fusion devices that I'm talking about. So people have made practical coils which can actually get to these magnetic fields. Well, what actually limits the magnetic field? You might say, high field is good. Why don't we just jack the field up to 100 Tesla? Well, you run into another limit, which is the strength of materials. The forces on the materials that you build your experiment out of depend on the magnetic field. They go up as you increase the magnetic field. And there's a limit. And there are structural limits for materials which are around a gigapascal. 1 atmosphere is 100,000 Pascal. So that's a pretty high stress, and those limits are somewhere in the sub 1 gigapascal range. And that leads you to limits of somewhere in the low 20s for Tesla for a practical device, which means that the field in the center of the plasma, which is about half of that, will be around 10 Tesla. That's twice the magnetic field of ITER. That's why we can make the machine about half the size, or maybe a little smaller. Understanding these mechanical stress limits is actually a very mature engineering discipline. So there aren't huge uncertainties in actually designing this. We know how to do this. This is well studied. It's basically materials properties for materials we already have, and it's classical mechanics. And so there are no mysteries there. So we know how to do this. I would also note that Alcator CMOD, which is the tokamak we've got on the other side of campus here at MIT, doesn't use superconducting coils, but it does use jointed coils. It's a copper coil, but we run at these kinds of magnetic fields, and we've run thousands of cycles at these very high fields with demountable joints. So it can certainly be done in terms of carrying the current. We now have to carry it over to the superconductors and make that an engineering reality. And we see a path for doing that. So what does this buy us? Why do we think this is going to help us so much? Well, let's think about development path. And here, by analogy, I want to look at what happened in nuclear fission in the 1950s. How was fission actually developed from a scientific idea in the laboratory to a practical energy source? And one of the key steps was to have a pilot plant, which is a scaled down version of what you can conceive of as a commercially viable device to make power. And this was done at a place called Shippingport, I believe in Pennsylvania. And they made a plant which made a few hundred megawatts of thermal power. It had a volume of about 60 cubic meters. Its cost corrected for inflation was under $1 billion in more or less today's dollars. Cost per volume was about $10 million per cubic meter. That turns out to be a pretty universal number for high-tech stuff, especially first of a kind. That's about what it costs. That's why reducing the volume on your development path is so important. You reduce the volume, you reduce the cost, it becomes much more manageable to actually make these things happen. It took about 4 years to construct the shipping port pilot plant. We can compare all these things with ITER, and the only number that's similar is the cost per volume. Because the volume is so large, everything else goes way up. And this number of 20 billion is probably a fairly significant underestimate for the real final cost of ITER, which is likely to be more like something exceeding 50 billion. Construction time for ITER is taking more than 20 years, and still counting, actually. ITER is an invaluable science experiment for getting at this burning plasma issue that I was telling you about, but it's not an optimized size for a modular pilot. It's not getting us there as fast as we could go. This is not to fault the ITER design. ITER was designed when the high-temperature superconductors basically were not practical. They were a laboratory curiosity when ITER was designed, so you couldn't design them into a real device. Now we think we can. Small size and modularity are self-reinforcing. You get there faster. By the way, you make mistakes along the way. You learn from those mistakes. You have to be able to iterate. Shipping port actually had 4 different designs for its core that were tried. ITER is a single point design. We need to be able to move quickly and try different things, because we know not everything we do is going to work the first time. That's another reason why it's so important to get the unit size and cost down. So what about this confinement physics, holding on to the energy, holding on to the plasma long enough to make it get into this self-heating regime where we can use it as an energy source? Well, we understand very well how this works. And I don't want you to worry too much about these equations, but basically there's fusion gain, which is related to this pressure times time. How high a pressure can you make your plasma and how long can you hold on to it? And it turns out these are plasma physics things that we understand and can't really improve very much. And then there's size of the device, roughly linear, and B cubed. So if I look at that and say, well, what do I want to increase to get my fusion power up? The size of the device, where the cost is going to go like R cubed, or the magnetic field, where the performance is going to go like B cubed. It's kind of a no-brainer if you have the technology. Similarly, power density turns out to be a really important consideration for economic efficiency. How economical will your power source be? It needs to have high power density. Once again, same thing. If you make it bigger at fixed field, you get higher power density, but slowly. If you raise the field, it goes like B to the 4th. So all of this says, let's raise B a factor of 2. So now we've got a factor of 8 there and 16 there. Those are really big numbers. They matter a lot. And they bring this cost down. So we knew how to do this in a pulse device using copper. Can we do the same thing with high temperature superconductors, high field superconductors? And the answer is we think we can. So Dennis White, who teaches a course in reactor design in the Nuclear Science and Engineering Department, assigned to his graduate students the task of what could we do with these high temperature, high field superconductors that would make the same fusion power as ITER in a much smaller package? And the students came up with this design here, which is called ARC. It's made out of these advanced superconductors, the high temperature superconductors. It's roughly the same size as this copper device, but it can run in steady state. And because it's superconducting, it can make net energy, and in fact, it can make net electricity. That's the design. For that, and that's the comparison here, steady state, no. Pulsed, yes, for ARC. Also, there's a blanket here, and there's an advanced liquid blanket, which is another thing we've been thinking about. I won't talk too much about. But that's also, you remember I said we have to make the tritium, so you need a good blanket. For a long time, people have mostly been thinking about solid blanket materials. There's a lot of engineering challenges with that. If you can make it a liquid blanket, which we think you can, that actually will solve a lot of those problems. It also, at the same time, allows you to cool the whole system. So it's a very good package, actually. And you can breed your tritium. And you can make net electricity. Q here is the ratio of power you need to sustain the plant. Sorry, it's the ratio of the power you get out in electricity divided by the power you need to sustain the plant. So a factor of 4 is not quite commercially effective yet, but it's very close, and it would be a tremendous demonstration. I also mentioned that high field lets you get away from some of these limits where the plasma goes violently unstable. And we know what we need. We need a reactor where the edge of the plasma, right near the wall actually, has a pressure of about 1.5 atmospheres. That's, of course, at a temperature of 60 million degrees. So it's not very dense. The pressure is the density times the temperature. But it's very hot and quite significant pressure. And it turns out that the pressure limits go basically like 1 over the square of the magnetic field. So another very powerful lever arm for increasing the field. If we double the magnetic field, you get a factor of 4 basically of margin in staying away from your pressure limits. And this just shows a typical pressure profile that we would envision for such a reactor, where this is the core of the center of the donut, the part of the donut that you eat, and this is the edge near the wall. And actually you have to have a couple of things. One thing that we've learned is that in this region here, not quite in the center, but near it, out close to the edge, the slope of this curve in pressure goes roughly like the strength of the magnetic field. This is slightly oversimplified, but that's a pretty good 0th order approximation. So, and that's just exactly the same argument as making the gyro orbit smaller means you can make the device smaller. It's exactly the same argument. So if you increase the magnetic field, this slope gets bigger, so you don't need as much physical size to get to the same pressure in the center. Turns out you also need to do something at the edge here, a little trick that we call an edge transport barrier, because the pressure right here close to the edge actually then determines the boundary condition for the pressure in the center, because this is a fixed slope. So if you think of it, there's a pressure here, you draw kind of a straight line to the center, that tells you what the pressure will be in the center of the device. And the slope of that line depends on the magnetic field. So we want high field, we want a high pressure at the edge, and we can get, and that also becomes very unstable if the field is too low. So you've got to get the field up for that reason as well. That's why b squared is another really, so we've got b squared, b cubed, and b to the 4th all in our favor. So all of those things say we've got to raise the magnetic field. And we know how to do it. Now another challenge that we have that we haven't fully solved yet is how do we get the power that's going into this device out on the surface. Now power comes out in 2 forms. It comes out because the alpha particles carry about 1/5 of the power. And it comes out as neutrons, which carry 4/5. The neutrons escape the magnetic field, and they actually go right through the walls of the device into the blanket. So we have to handle that power in the blanket, and we think we know how to do that. The other 1/5, however, is absorbed in the very near surface, in the first few even monolayers of the surface of the device. And that's a high power density. So we've got to be able to deal with that. And if you think about making the device smaller, you would think that that problem actually gets worse, because now you're trying to take a lot of power out through a smaller area. But you have to scale things. As you scale down the size, you're also going to scale down the total power so that that problem doesn't get worse. It doesn't get better, but it doesn't get worse. And we haven't really solved it yet. And this is some detail of studies that we've done to understand how that power flows out and what area it actually impacts. When we put that all together, we see that in the parameter that matters, which is basically the power times the field over the radius, which is kind of fixed, I told you. If you raise the field, sorry, this goes up, but this has to go down. And when you do that, you end up in this range here for reactor designs. Existing experiments, with the notable exception of Alcator CMOD because it runs at high field, run at much lower, actually, power densities. So they don't have to really deal so much with this challenge. But when we get to making power in a reactor, we've got to solve this problem. And it's, as I've said here, it's about 10 times as hard as it is in most current experiments. So we've also proposed here at MIT a much smaller experiment to actually get at this particular problem. We call it the Advanced Diverter experiment. It would actually be basically the same size as Alcator CMOD. And we would build it in the same experimental hall. It would be a follow-on. And this is something that our community has recognized is important to solve this particular challenge. And the key here is you devote a lot of volume to the region where the power comes out, which is down in these legs here. I won't go into the details, but that's a very exciting, very near-term opportunity. And this just shows you some details of that, where the power has to flow out. And you need to devote some extra room to that so that you can deal with it. We also have to sustain the plasma in steady state. I told you at the very beginning of the talk that we take the magnetic field and we curl it into a toroidal shape. But if you do that with just straight field lines, it still doesn't quite work. It doesn't confine the plasma. You have to have helical field. To do that in the tokamak, we produce a very large electric current in the plasma itself, which makes a magnetic field perpendicular to the main confining field. When you add those two fields together, you get a helical, a twisted magnetic field, and that turns out to be what you need. So we also have to maintain the plasma current in steady state in the tokamak, and we do that, we think, using microwaves. And it turns out higher field also helps this. The whole process gets more efficient. The number of amps you can drive per watt of microwaves shined into the plasma goes up with magnetic field. And that's what this curve is. This is the efficiency in amps per watt as a function of the magnetic field. And you can see another big win by doubling the magnetic field. There's another approach, toroidal approach, called the Stellarator, which is in some sense competing with the tokamak, or maybe a backup option, where you don't actually have to drive current in the plasma. You make twisted field coils to get a helical field. That has advantages and disadvantages that I won't go into today, but it turns out high field, high temperature superconductors could also be revolutionary for stellarators, and this is just one design that people in Japan have been looking at to take advantage of this with the Stellarator. Conventional designs for pilot plants and reactors have, up until now, assumed very aggressive confinement physics, operating very close to the pressure limits. And we had to do that because we couldn't be any bigger. We were limited. So we had to have very high normalized pressure to make this look attractive. It's not to say it can't be done. We think it could be done, but you have a lot less margin for error. The plasma is much closer to the stability limits. There's another problem with this design, a conventional superconductor, which is you can't have joints in your superconductor. Remember I said you have to wind the coil and then you have to heat it up to make it superconducting. After you do that, there's no way to disassemble the coil. You're left with basically extremely brittle materials that you can't disassemble. And that means that if you inevitably have to do maintenance on a device like this, you have to pull everything out through these ports. So you have to go in, you have to cut all the welds for all the systems, probably tens of thousands or even hundreds of thousands of welds, pull out units through the ports, replace things that have broken or renew equipment. It's basically repetitive building of a ship in a bottle. This is a very challenging thing. But if you can have joints in your coil, as we do on Alcator CMOD, now you can imagine a design, and this is ARC again, where you can actually disassemble the machine and pull it apart modularly. And now you don't have to, it's no longer a ship in a bottle. It's completely take it apart, fix it, replace the parts that you have to replace, put it back together. You can also build these things now off-site using advanced manufacturing techniques. You could 3D print this vacuum vessel at a factory, bring it, plop it in, then assemble your magnet around it with the jointed magnets. If this thing gets damaged during operation, you can pull it out and have a spare. So it really is game-changing just to have this modularity and ability to disassemble. This just shows from the student design the stresses in the magnet for the design that they came up with, showing that it stays below the stress limit of the conventional stainless steel. We have in the world a tokamak called JET, which was built, it's still operating, it's in England, it's a European project. It's near London, near Oxford actually, and it has made 10 megawatts of fusion power. And it runs with copper coils. And it has a maximum magnetic field of about 2.5 Tesla, maybe 3 Tesla. So we can triple that magnetic field with the new superconductors, and in a device which is basically the same size, these are to scale, instead of 10 megawatts of fusion power, because of this B to the fourth in the fusion power production, we can make 500 megawatts of fusion power with that device. In something which is the same size, this took about 4 years to construct from start to finish. And actually, in the world, we've built 3 experiments, 3 tokamaks of this size, all of which were built in under 4 years. One was done at Princeton. It's called the TFTR, which operated in the 90s, and another one in Japan. So we know how to build things this size, in this geometry. We just have to replace the copper with the superconductor. We think we know how to do that. So what should we do? In the near term, small-scale research can and should pursue this exciting path. I told you about this diverter tokamak, diverter test tokamak. We want to figure out how to make jointed coils, put it all together into this thing called ARC. Now on Thursday, I believe, Brandon Sorbaum is going to give a talk over at our center in NW17 about something even smaller than ARC, what we've called SPARC, soonest possible ARC. It will not be a net electricity producer. It would be even smaller than this, but it would be a net energy producer. So that's something we're also thinking about, and I encourage you to come to that talk as well. But again, it heavily relies on this advance in the superconductor. So where are we? Superconducting technology, this advance has opened a new window for a faster path. The coils are a reality. They're not yet at the scale we need for fusion, so we need to do the R&D to get there. And I've already told you a lot about how important an advantage having a jointed coil would be. But we need to do this R&D. The physics basis, the plasma physics, is largely demonstrated. We do need some improved surface power handling, and I told you about the current drive challenge. But again, high field helps with both of these. So what should we do? Fusion is needed, and I would say it's needed soon. So we need to continually be looking for innovations so that we can accelerate the development. And we have something now available that we need to take advantage of. And we need to get going on this now. And then combine this in a net electricity producing pilot. And then fusion will no longer be a dream, it will be a reality. So thank you very much for your attention. And I'm happy to answer questions. Yeah.
You're talking about the jointed coils, and as I understand it, the joints are still going to be conventional conductors. Is that correct?
So what happens typically is you do have to have some interface between the superconductors which is not superconducting. And you have to manage it in a way where the joint resistance is sufficiently low and the power dissipated can be handled by the cooling. The power that you're dissipating in the joints is not a problem from the overall energy balance of the plant. That's not the issue. The issue is, can you cool the joints so that the surrounding superconductor material does not warm up and go normal? And that's another big advantage, and it's really another reason why the conventional superconductors are not amenable to joints, because they have such small thermal capacity. It's almost impossible to take out that heat in a conventional superconductor. It turns out it's not all that hard at 30 or 35 degrees K. Now, if you want to know the gory details about how this all works, Joe Minervini, who's sitting right there, can fill you in on how this all works.
What I understood from doing a little bit of reading on those tapes, you're soldering them, in effect.
In effect, that's one approach. You can also just actually use a pressure joint where you actually just compress the two tapes together. Of course, you use many in parallel. And you can get the joint resistance down to, I don't know what, nano ohms per connection. And that's already been demonstrated in the lab. So yeah, so that's, and that's the work of one of our graduate students who's working on that for his PhD. There are other people working on this as well, but that looks extremely promising. Yes?
What kind of funding is and where's the funding coming from? Presumably the federal government. And what level is it, and what do you need to make this a reality?
Well, those are a very good set of questions. Right now, the research in the United States is essentially almost all supported by the U.S. Department of Energy, including our research here on campus, at least most of it. Now, there are a few privately funded fusion development efforts in the U.S. There's one in Canada also. They are doing different approaches to the one I've talked about, and we could discuss that. It's interesting that there is private funding for fusion, and we're thinking about how we could leverage some of these new ideas to get private funding for this development. Right now, the Department of Energy is not, I would say, very receptive to these kinds of ideas to be supported, because they have to worry about how they're going to fund ITER construction for the next 10 or 20 years. So that is consuming most of their, I would say, mental energy right now.
What kind of construction did you say?
The construction of ITER.
Reader.
ITER.
Oh,
ITER product. ITER. ITER is how we pronounce it.
The French.
It's being built in southern France, but it's a worldwide collaboration. The U.S. is responsible for about 9% of the ITER scope. And that, in addition to smaller scale experiments around the U.S., is consuming all of the available resources right now. But we think we need an alternative path. So we're talking to DOE about this. And they listen politely, but they don't give us very positive feedback yet. But this could change very quickly. We don't know. And we are also starting to reach out to private industries and also philanthropists who we think could be very interested in funding some of this research. In terms of the amounts that are needed, it's a little tricky to answer that question. But the machine ARC that I've shown you is a billion-dollar class facility, probably a few $1 billion. Don't pin me down to that number right now. We don't have a detailed engineering design yet. But based on its size, that's about what it should cost. The jet experiment that I showed you was roughly a $1 billion facility. Now, it's not superconducting. You probably have to pay a little more to make it superconducting. But as I showed you, cost per cubic meter or cost per pound is roughly constant for these kinds of facilities. So we have a, that's the order of magnitude. The whole process leading up to that is multiple billions, but it's not 100 billion. It's maybe 10.
If I remember the slide, ITER is expected to come online in 2030.
There is no official schedule at the moment. The most recent sort of sanctioned schedule had first plasma in 2019 and then actual fusion power in 2027. We know that that schedule will not be met, but by how much it will be delayed is not yet, shall we say, official.
Until you change their mind, the presumption is that DOE funding will be tied up till that.
A lot of it is. A lot of the funding and a lot of the sort of intellectual energy is tied up with that right now. I'm not saying ITER shouldn't be done, but it shouldn't be the only thing we do. Yes?
At this point, is it still possible to do any changes to the design?
It's really too late. I mean, you can tweak certain things, and they're looking at, adding a little trim coil here or there to deal with a problem that they think might come up. But the basic design is frozen. The superconductor has all been produced. And they're starting to wind it into coils. It's really too late to make any kind of major change like the one I'm talking about. You can't do that at this point. It's taken, the ITER project really began officially as an international construction project in 2006. It had been an engineering design activity for 15 years before that. So most of the engineering decisions were baked in the early 1990s. And it's really much, much too late to change those at this point. Yes, Dennis.
So, hi. Hello, everyone. So I just want to make an announcement or an advertisement. If there's any students, undergraduates or graduate students, who are interested in taking the next version of the design class that made that, it's starting actually in a few weeks. 2263 is the course name. So if you're interested, you can drop me an email. I'm easy to find.
Okay. Yes.
It's possible to give a brief overview of the alternative approaches that are being taken, commercially funded approaches that are drastically different, maybe smaller.
Sure. So there are a couple of private companies. There's one in California. There's one in British Columbia. And what I would say generically about them, if you think back, go back to my, I'll go to this view graph here. And I had said that this is the plasma physics that we basically understand and we don't think we can improve very much. Their approach is to say we can improve this enormously. That's their approach. So they are not going to high magnetic field. They are saying we can work, I won't say miracles, but enormous increases in the plasma physics performance. If you ask my personal opinion, I think it's extremely low probability that those approaches will work. It would be great if they did, but that's not where I would put my money. Yes?
Is that data the same data that you have on the slide as defined as the pressure over the base for the
It is. It's b squared. But yes, the beta is the ratio. Well, this one is actually slightly, there's a subtlety here. You see it says beta n. I don't want to get too much into the gory details of the plasma physics. This is the beta that I was talking about, further normalized to how much plasma current or how twisted the magnetic field is, basically. And it has a size scaling built into it as well. So it's slightly different, and it is actually the beta that determines the stability limit. That was a kind of a subtlety that I didn't feel was necessary for this discussion, but it's related to beta, but then it's further modified so that it's no longer a typical betas the beta I defined as pressure over B squared is typically in the 1 to 10% range for stable plasmas. This beta n then becomes 1 to 5 is kind of the range where you can operate. And the arc, I think, operates somewhere around 2. And those other kinds of reactors operate around 5 for beta n. And that difference of 2.5 means that instead of being away from the cliff, you're right on the edge of the cliff. Yes?
So if there are such huge gains from increasing magnetic field, perhaps for fusion, we should be looking at high-temperature superconductor research and physics research rather than fusion plans as a way forward?
So that would be true in 1980. But the basic physics that we did in 1980 has gotten us to the point where we think we can apply it now. So I'm not saying basic physics is the wrong thing to do, but we don't need to go beyond this in magnetic field. And in fact, we probably can't because of the strengths of materials. Now, if you can come up with a material that can withstand twice the stress, and maybe there are ideas for doing that, certain advanced ceramics and things, that would be another area where you could conceive of making yet another leap. Now, there's another thing that limits us from making the machine too small that I didn't talk about, which is the mean free path of that neutron coming out of the reaction. It turns out, no matter what you do, that neutron travels roughly 1 meter in almost any material. So that actually sets a lower limit to the size of your fusion reactor. You have to have approximately 1 meter of blanket surrounding the plasma. So even if I could make the plasma the size of a pea, the machine would still be several meters. There's just no choice. So at some point, it's a kind of, the returns are not worth the trouble. But better materials would be a good thing. And superconducting magnet research to make them better, for example, the joints or things like that are certainly something we should be doing. In terms of other physics research, I'm all in favor of doing it full bore. My appointment is in the physics department, and that's what I do for a living. So we need to apply it and continue to push the frontiers. So we need both. Okay, well, thank you very much for your attention.